Okay, hello and welcome to Lab 2. Let's talk about it. I hope I'm in the right folder, yes. So before we get to the write-up, I would like to tell you about pairs in C++. Okay, so there's this nice helper documentation site on pairs. All a pair is just two things at once. It's holding on to two things instead of making two separate variables called like x and y, holding like 42 and true, that the types can be different. You are instead you can place them in a big pair, right? You'll make a big pair. The type looks like this. It lives in the utility header, but its pair is templated by the two things that go inside. So this will be like a pair of an int and a bool. All right, you can say make pair. There's a function that creates a pair like this. You give it the two things, and it will make a pair holding both those x and y things. Okay. So it'll make your pair P look like this. It will hold on to the 42 and the true all at once. And those pieces will be called first and second inside of a C++ standard library pair. So you want to get the first thing that you put in, it's dot first. You use the second thing, it's dot second. Okay, so that's how you use pairs. And so it's make pair to create one. And like here's an example. If you click on it, it's like I'd like to make a pair of 10 and 20. I'd like to make a pair of 10.5 and A. So it's going. You would want this to be like usually as a pair of a double and a char, but I guess it's been declared already to be an int and an int, and so it'll convert it. But normally you want it to be two separate types a lot of the time. Okay, so that's how you make a pair of things using the make pair function, and to get the pieces out, you use p dot first and p dot second. So now let's talk about the write-up. Okay, so first thing first I want to say is that you can work in pairs starting from this lab onwards, all right? I don't think I'll disallow it, but from now on you can work in pairs, a group of two only, no more than two, on your lab. So I'd like you and your partner, once you find one, to please still submit your code separately. That's much easier for me to give you a grade. Just let the autograder do its thing still. But what I want you to do, in addition to both submitting to the autograder, include a comment in your code saying who your partner was, so that when I see identical code, I won't have alarms going off in my head. So yeah, let me know if you need any help with transferring your code between you and your partner. I have some ideas that I can talk about with you, and I can help you with that. And you're also, of course, allowed to post on Discord if you'd like to search to find a partner. That's a great place to look for one. So you're allowed to do that from now on, starting from this lab. Okay, so find a partner if you'd like, but of course you're still welcome to work alone if that's better for you or more convenient. So the first part, of course, is to get your code. Here are all of the pieces. You have a make file again. So as usual, let's look at all the stuff. So even though we may not have gotten to, in lecture, all the stuff, we're going to implement RSA. It's an encryption algorithm called RSA. You'll be reading about it in your book. We'll be talking about it in lecture. Even if by the time you're watching this video you haven't seen every piece of information about the entire RSA algorithm, you can do most of the pieces right now anyway. Okay, a lot of it is stuff we've already talked about. So you're going to implement all the functions listed in rsa.cpp. All right, shouldn't be too bad. This lab. So here's rsa.h. You're going to implement all these things. So all these are pieces of the RSA algorithm from your textbook. So you can go read ahead if you like, but you'll eventually get to it, and this is what you'll be implementing. So there's a piece there's an n that you compute with a p and a q integers. There's a phi that you compute. You do pow mod. That's something you could probably compute right now and figure out. It's just x to the power of y mod m. That's an algorithm you can come up with. You definitely know by the time you're watching this video how to compute the GCD. This will involve the extended GCD, so all this will make sense once you learn everything about RSA, but you can do a lot of the pieces right now. Here's the extended GCD. This is the one that involves pairs. So you're going to get two numbers, and you want to find, you want to do the extended Euclidean algorithm. You want to find the integer that you can multiply x by and the integer that you can multiply y by, that you can add together, your linear combination that creates the final GCD. So this will return a pair of two things, a, b, such that a x plus by equals the GCD. So you're going to have to code up the extended GCD algorithm. And then you can use that to generate the multiplicative inverse of two numbers. So you'll have to use this one to make this one happen. And then there's RSA encryption and decryption. We're going to be encrypting just numbers. Because what is everything in computer science anyway, inside of a computer? But ones and zeros is just a big number anyway. So your message and your ciphertext, this will all make sense once you learn more about RSA or read about it. But these are all the pieces, and a lot of them you are capable of doing right now. So that's the header file. You're going to implement all that stuff in the corresponding CPP file. So I've given you like little stubs for everything. You'll have to make it all work normally, of course. All of these are the wrong answers, but just follow the comments. It should make enough sense. For all that, what else do I want to say? Going back to the write-up. Yeah, so the book will be pretty much everything that you need. The book is going to tell you enough about how to implement all of these functions, except for maybe the extended GCD. Okay, so there's a Wikipedia page on that one. I think I have a slide about that as well. So you're going to be doing the extended Euclidean algorithm, otherwise called the extended GCD algorithm. And so you got to find that x and y such that a times x plus b times y is GCD of a and b. That's the idea. So you just find those two things. I think I should be saying, if I follow the instructions from here, it's supposed to be find the a and b from the x and y. So I think I wrote it backwards. So x and y, find the a and b. But either way, it's still the same. Still the same idea. Okay. So that's your extended Euclidean algorithm, and that's what you're gonna code up. And there is some pseudocode on the internet for that. If you just go to this Wikipedia page, so that's there. It's also linked here. You're going to return a pair of these two things starting with these numbers. And what I recommend, if I zoom in here, what I recommend is to implement the following. Here's the pseudocode section. And so what you want to do is implement one of these, like extended GCD, this one, extended GCD, this one. I think either one is fine, but what you're going to give back are these coefficients, these Bezout coefficients. That's the equivalent of saying you've calculated those things for the GCD. So that's the sentence saying that. So you're trying to output, you're going to return at the very end old S and old T, that pair. Okay, that's what you're going to do. So that's what you're going to be computing. And this is the pseudocode. This is a weird little bit of pseudocode. It's like it's working with pairs. This is like making a pair called, it has the first part being old R and R, and then it's holding on in the first part A and B. So this is like it's setting two variables at once to these two values. You see that? It's like setting old R to A and and then B, old R becomes A. It's like saying that, and then it's also saying R becomes B. See that? So these are called parallel assignment statements in the pseudocode. It's like doing both of these things at the same time. Okay, it's equivalent to this code. So think about it that way. You might run into some issues if you try to code this in, like, you just say like, okay, old R equals R, and then R equals old R minus all this. Because no, it has to be the old R. It's very confusing. Okay, so just think about that. This is a parallel assignment. Okay. So these are both happening at the same time. Old R becomes R, and then also R becomes the old R at the same time. Okay, so read more about that because you might overwrite things a little too soon. So just look into that. It really you have to do something like this. It's really a 3-step process rather than just a 2-step process. Okay, so you'll code all this up. Eventually R will become 0, and you're given back the old S and the old T as your answer. Okay. So that's the idea. Another way of implementing that is this code right here. It also gives out these coefficients. Again, it's going to use those parallel assignments that you'll have to read more about to get them right. Okay, but either way, implement one of these pieces of pseudocode, and that should be enough. Okay, just be careful about this line. It's not what you think it is. Got to read more about it. So that's that. I think that's what I said. So you'll use extended GCD in your multiplicative inverse function because you're going to try to find the inverse of something. So the extended GCD should be computing 1, of course, but you're going to find those two coefficients, and then you're going to pick out the coefficient that you needed, okay? Because 1's going to go away once you do the mod phi, okay? So that's the idea. Another thing I want to say about the multiplicative inverse is that remember your answer must be, you're doing mod phi, so your answer must be between 0 and phi minus 1, okay? So if your number is too big, it's bigger than that, or if it's negative, because your coefficient could have been negative when you ran extended GCD, you have to convert it to be an equivalent number, mod phi, within this range, okay? So read this hint as an example. All right, that should help you enough. But yeah, I've got a bunch of tests for you, just implementing all these functions, essentially reading it off of the book once you read all about RSA and you learn all about it. I've made a bunch of test functions that make it all work out, and here I am encrypting some numbers and decrypting some numbers, okay, with some certain starting values, okay? So I'm encrypting random numbers. Why not? So that's the idea. And then you could compile this with the make file, say make test RSA, and then that will make an executable file that you can run, and it runs the tests. Once those pass, you're all good. Okay, so just remember to get started a little bit early so that you have time to have it all sink in, and then the only file you're messing with for this lab is rsa.cpp, the implementation of everything in that header file. So the tests are all completed already for you. The header file has everything you have to implement. Just go to that CPP file, make those bodies have normal answers, and you are good to go. So yeah, that's RSA. Shouldn't be the world's hardest lab. It's just reading most things off the book, but it's a very fulfilling thing, I would say, to get it working, because like this is what is underlying all of the internet. Like if I look at this connection to Canvas right now, like why is this connection secure? It's through, you can like view the certificate. You're going to see the word RSA pop up. It's a very, very common thing that's just makes the internet run. So now you know, now you're making it yourself. So yeah, that's your lab 2. I think that's all that I wanted to say about it. Please yell at me if you have any questions. And yeah, I'll see you next time.